Okay, so yeah, it's broken up by topic. So number one is going to be um, like derivatives of exponential and log. And then there's also some hyperbolic stuff and inverse trig in there. So it's just derivatives and chain rule. And then part two is logarithmic differentiation. But on the exam, I probably wouldn't tell you use logarithmic differentiation. So you'd have to be able to recognize the technique. But I thought if I put it in the review and told you what to do, it'd kind of help you. So, and then three, max min. I mean, so there's a bunch of problems here. It's just more like practice here, you know. And then number four, the first two? Okay. Yeah, number four is mean value theorem. 5 is graphing. 6 is, no, 5 is local max min, increasing, decreasing. 6 is graphing. 7 is an optimization problem. And then number 8 is all L'Hopital. Yeah. So y'all want to start with 1? All right. I'm good. Got it. Thank you. All right. You want me to start with the first one? A? So what is your thought on this? What are you thinking needs to take place here? Okay, so the x sine x, you look at that as a product. You can see that that's a product up there, but it's in the exponent of an exponential function. So if you look at like chain rule, remember chain rule works that you work from the outside in. And so here it's kind of weird because what's the outside? Well, to remember how to determine what the outside is, just think about if you were to plug in a value of x right now. If I said plug in 0 or something like that, you would figure out what all this is first, right? And then you would take 5 and raise it to that power. So the last thing happening is the 5 to the power, right? That's the first thing you're going to differentiate. So the question becomes, you know, what is the derivative of 5 raised to something? I'll call it u, right? What's the derivative of this? Well, on your formula sheet you have this, but hopefully, you know, over time you've come to realize that the derivative of exponential functions are itself, but then chain rule says times the derivative of what was up there. And then that's where the product rule is going to come from, right? So I'm going to be able to rewrite this, you know, as its derivative will be 5 to the u, which in this case is the x sine x. But then I need to multiply that times that u prime out here, which is the derivative of that x sine x, right? So maybe on the side here, write down your x sine x. You know, that's your u, basically. The derivative of that will be your product rule. So what is the derivative of x sine x? Derivative of x, which would be 1 times sine x, and then plus, which is cosine x, and then times x. And I'll just clean that up. That's sine x. We always like to put that x out in front of the cosine x, only because we don't want to put x next to x and people think that that's x squared, right? This x is in the cosine, this one's outside. So this is a better notation. That just gets stuck right in there, and we're done. How about the next one? Do you want to just go through, since you said you struggle with part 1 and 2, just do those, do like all of those, and then go to L'Hopital, and then just whatever else we have time for? Okay. I can stay till about 1, so y equals, but I might have some pre-cal students showing up also. They have a test on Wednesday. Yeah. You don't know. It's still early. I know I do have students that said they were going to show up like 10 o'clock, 10:30. So some people had classes today. Yeah. So sine inverse of x squared plus 1. So again, chain rule, right? The last thing happening is the arc sine. So you need to go and figure out, what is the derivative of arc sine of something. So you'll probably need your formula sheet. Do y'all have it? Anyone have it with you? Break it out just so, no, it's all right. Just so if someone has a hard copy, just so everyone can look off it so you know where to go to find it. Because you don't want to be like trying to hunt for it on the test date. It's a lot. Yeah, well, again, it's just to give you a lot to practice. So you want your derivatives will be on page 5, and your derivatives of the inverse trig functions are here. So derivative arc sine of x is this. All right? You don't, because you can have that, right? So it's -1 square root of 1 minus, now I'm going to put u squared because I'm using u instead of x. But then chain rule would then tell me I now need to multiply that whole thing by the derivative of whatever was in there, whatever was inside this trig function, right? Just like up here, derivative of 5 to the u is itself, but then times what derivative of what was up there. Derivative of arc sine of u is the formula, but then times derivative of the u. So for us, we need to figure out what u is. U for us is just x squared plus 1, so u prime would be 2x, right? So let's write this answer up. The derivative here would be -1 over the square root of, now be careful here, what is this going to be? 1 minus what? X squared plus 1 quantity squared. See, because our u is actually x squared plus 1, right? So that's what goes into the formula. And then next to it times the derivative of u, which we said was 2x. Hey, here's a copy of the review. Okay, and there's some tacos here. It's first come, first serve, so -2x. We'll break out the margarita machine around noon. All right, so that's it right there. All right, moving on. You just let me know if you'll have questions. I mean, this is, in this setting, we can stop. We can talk about things if we need to in more detail. Okay, cosine hyperbolic, sine x, all underneath the square root. So what rule am I going to apply to this one? What's the last thing happening? That's the first thing happening. Square root, right? So I've got to start with that. All right? So I say to myself, what is the derivative of the square root of something, right? And I've tried, I don't know if it's worked or not, but I've tried to get y'all to just realize it's 1 over 2 root u. But then you always have to say times the derivative of u, right? Now for us, in this problem, u is everything under here, right? That's u, right? That's my u, that's my u. So I'll need its derivative out there at the end. When I go to take the derivative of u, I'm going to have to look at this entire thing and realize that's another chain rule, right? So I'll have to work with that. So let's write down what u is right here. U is equal to cosine hyperbolic of sine x, right? So treat this like its own problem now, all right? If I ask you to figure out what's the derivative of cosine hyperbolic of, I'm going to use w instead of u, right? What's the derivative of cosine hyperbolic of w? Do you all understand what I'm doing here or not? Kind of? It's not a product. It's because cosine hyperbolic is a function. It's a function. Now, if it said cosine hyperbolic x sine x, then it would be a product rule. So you have composition, one function inside of the other. So we have to do chain rule again. So I'm looking at this cosine hyperbolic of sine of x as being cosine hyperbolic of something. What is the derivative of cosine hyperbolic? So again, you now go to your hyperbolic trig function derivatives. Is a review? Need a review? We're just going through this. There's tacos if you're interested. Okay. It's sine hyperbolic. In this case, it would be sine hyperbolic w, right? But then because of chain rule, times the derivative of whatever w is. Whatever was inside of it, I have to take its derivative, which is, that's an obvious one, right? I hope. So I've got like three things going on here. You know, the last thing is w is equal to sine x. So w prime is equal to cosine x. This is u prime. Okay, so let's see if I can put this all together. The derivative of y should be, first of all, what? The derivative of the square root part, which was this, right? So it's 1 over 2 root, but what's u for us? Cosine hyperbolic of sine x, right? But then chain rule says times u prime, right? Times, now what's u prime? U prime is right here, right? It's sine hyperbolic of w, right? But w was sine x. But then times w prime, which is cosine x. And that's pretty much it. Yeah. I mean, you could put the sine hyperbolic sine x times cosine x. You could put it all on top up here, but it would mean the same thing. Let's look at D. Y equals log base 4 of square root of x squared plus 1. All right, so what is the last thing happening here? The log base 4, right? So I need to go and take a look at this. If I ask you, if y is equal to log base 4 of, let's say, u again, right? Then what is the derivative of that? So you go to your formula sheet. What is the derivative of log base a of x? No? See it on there? One over x natural log A. Should be on the derivative formulas. See it? Okay. What's the derivative of natural log of x? Natural log of x is just 1 over x, right? But if the log is something other than a natural log, then you always have to tack on this little part right here. This natural log of whatever the base was, 4, 10, doesn't matter. So up here, what is it going to be? I have 1 over, not x, but what? 1 over, my variable is u, right? U, natural log 4. The derivative of log base 4 of u is 1 over u, natural log 4, by the formula. But because there's chain rule involved here, I then multiply that by the derivative of whatever u was, right? Okay, now, let's talk about what u was. U was what? Square root of x squared plus 1, right? Hey, you have a review copy? No? Reviews and tacos if you're interested. Yep. So if you don't eat them, someone else is going to eat them. So the question on u is, can you take the derivative of u, or are you going to have to break it down further? That's all up to you. It depends on you. Not you. It depends on you sitting there in the room, okay? It's another chain rule, right? So if you really want to take this slowly, you could say, I'm going to say that that's the square root of, let's say, w now, right? What's the derivative of the square root of w? 1 over 2 root w. But then because of chain rule, what do I tack on to the end of that? Times, careful, w prime, right? You're doing it all in one step. That's fine. Does that make sense? Okay, but since you broke it down further, you have to tell me what w is. In this case, it's x squared plus 1, and you're going to need to be able to tell me what the derivative of that is, which in this case is 2x. So let me try and put this all together now, all right? I have that the derivative is, and you can see it right here, the derivative is going to be 1 over u, but what was u? It was everything in here, right? It was the square root of w, but w is x squared plus 1. So this is going to be square root of x squared plus 1 times, down here, ln4. ln4 is just a number, okay? It may as well be the number 10. It doesn't matter. It's a number, and it's just going to be there. Then I say times u prime, right? Come on in. U prime. So what's the derivative of u? It's 1 over 2 root w. So 1 over 2 square root of w, but w is square root of x plus 1, right? Times w prime. W prime is 2x. There's a few things that we can do here algebraically, even though if you got that on the test, I would be pretty happy with it. But these twos can reduce out, right? I could also put the square root of x squared plus 1 times another square root of x plus 1. The roots would multiply and go away, and you just get x squared plus 1, right? A root times the same root is the root squared, which would get the root out of there. So this would really turn into the x that was on top, the x squared plus 1 that was left when I multiplied those together, those roots, and then I'd have that natural log 4 down there. Do you need a copy of the review? There's also tacos, and if no one eats them, I don't know what's going to... There's tacos. It's going to make me hungry. Mm-hmm. All right. I just want to show you something. There was a different approach for this problem that would have gone a lot faster. Okay, let me just show it to you real quick. The original problem was y equals the square root, log base 4 of the square root of x squared plus 1. I could have rewritten the square root as raising to the 1/2, right? That's the same thing. And then we have now I'm not doing any derivative right now. I have a property of logs that says that if I have a power on something in a log, right? If I have log of something and that something here is raised to a power, I'm allowed to drop that power out. We use that quite a bit with logarithmic differentiation. So if I take that 1/2 out before I do my derivative, then I can avoid having to do that middle step right here, because I won't have a square root anymore. So now what would happen is the 1/2 would just stay with me the whole time, right? Because it's a constant. The derivative of log base 4 of something would have been 1 over that something, natural log 4, times the derivative of what was in here, which would have been 2x. And that would have been it. I would have been done, and these 2's would have canceled, and I would have got, what, x over x squared plus 1 times natural log 4, which is the same thing here. So just FYI. All right, next one. For those of you who came in and I'd already started, everyone that was here at the time had said that the problem spots were like number 1, and then the very last page is all L'Hopital's rule. So our plan here is to go through number 1, every single one on number 1, and then go straight to L'Hopital's rule and do all of those, and then start going through the rest of these. All right, and maybe what we'll do after that is we'll just do like 1 from number 2, 1 from number 3, 1 from number 4, 1 from number 5, 1 from number 6, and then just cycle through until we're out of time, I guess. All right, so log base 7 of x squared over x squared plus 1. I guess I really liked the x squared plus 1 last night when I was putting this together because it's all over the place in this thing. All right, so they're very similar to the last problem. Very similar. I can look at y as being log base 7 of something, right? Call it u. So the derivative of that will be what? 1 over u ln 7 times u prime. And then I need to be able to determine what u was. U was what? X squared over x squared plus 1. Now, is that x squared over x squared plus 1 something that you're going to have to break down, or are you comfortable taking that derivative? You comfortable with that? It's a quotient rule, isn't it? So I don't have to, it's not composition. That's what I'm getting at. In the previous problem, when we got to the point here with u, right, we looked at u and we said, wait a minute, hold on, that's composition, so I'm going to break u down even further. On this problem, when I look at what u is, I realize I can take the derivative of that all in one step, so I'm not going to try and break it down any further. So I'm just going to call u exactly what it is, x squared over x squared plus 1. And then I will take its derivative, and to do that I'll use the quotient rule, which says it's the derivative of the top, right, 2x, times the bottom, minus the derivative of the bottom, which is again 2x, right, times the top, all over the bottom squared. Is that all right? I'm going to clean that up. All right, it's going to be, what, 2x cubed when I distribute through, plus 2x, then what? Minus 2x cubed? So they'll cancel out. I'll have that 2x cubed in the front, we'll cancel with this, so the only thing left will be a 2x up there. So u prime is equal to 2x over x squared plus 1 squared. And that's everything I need to put this thing together. Any questions? Y prime equals, let's see, y prime is equal to 1 over u natural log 7. So 1 over u, but u is x squared over x squared plus 1 times natural log 7 times what? This u prime, right? Okay, so 2x over x squared plus 1 squared. Now that's the raw derivative, but there's definitely some simplification that can happen here, some cleaning up. Watch this. The 1 over natural log 7, like that, that's just a number, right? So I'm just going to pull that out in front, which leaves me with this right here, right? A 1 over that. But 1 over a fraction is the same as the reciprocal. So I could rewrite that piece as x squared plus 1 over x squared. And then at the end over here, this piece is 2x over x squared plus 1 squared. So what do you get here? What happens here? Do you see it? One of these cancels, right? And then one of the x's cancels. Right, x over x squared leaves you with an x on the bottom. The x squared plus 1 and then an x squared plus 1 squared, one of them cancels also. So what would I be left with then? 2 over ln 7 and then the x squared plus 1. And that's it. Yeah, I don't know. I didn't hear anyone say x, so yeah, sorry, x. Yeah, that x is here. And that's multiplication in there. I don't like the way that's written. Times x squared plus 1. Now, this took a little while to do, right? I mean, there was a little bit involved. I'd like to just show you again a slightly different approach to this problem, which would demonstrate a little bit higher level of thought, I guess. If I would have approached this log base 7 x squared over x squared plus 1, and I remembered this property of logs, it's a property that says that if you have something divided by something inside of a log, you can split this into two separate logs with subtraction between the two logs, like this, right? That is a property of logs. So since I have something over something, I could have just started the problem without a derivative yet and just made it log base 7 of x squared minus log base 7 of x squared plus 1. Since they have the same base, could I do what? I'm not sure what you mean by take away a log. No. And here's why. Again, because this is not a number, it's not multiplication, this is a function. So you do not distribute logs through parentheses because it's a function. It's like when you have sine of something. When I say sine of x plus 2, that does not mean sine of x plus sine of 2, right? It's not distribution. So it's the same thing here. This does not distribute through. That's a good question. I mean, no, I didn't mean that. You didn't mean that. Uh-huh. Oh, oh, I see what you're saying. No, because, I mean, look at where it came from. This is the property. The property says the only way to go from one log to two logs is if you turn division into subtraction. So you can't go back now and turn subtraction back into a single log unless you turn it back into division. So, but see, what's nicer about this one is that I have two different terms and I can differentiate each one separately. So what is the derivative of log base 7 of something? So I'm taking my derivative here. It would be 1 over x squared times natural log 7, right? Times chain rule, derivative of what's in here, 2x. That's the derivative of this. Then I say over here, minus derivative of log base 7 of something is 1 over, that's something, right? X squared plus 1, natural log 7 again, but then times the derivative of what's in here, which again is 2x. And you can cancel this x and this x, right? Which becomes 2 over x ln 7 minus, over here you cannot cancel the x, so 2x over x squared plus 1 ln 7. That is done. The answer does not look like the previous answer, but it is the same answer, all right? The way you could get this to become that up there is to just get a common denominator, but we're not going to do that. So either way would work here, all right? All right, let's look at the last one, F. So y is equal to e to the cosine x plus natural log x. Now I could just go and just grind away at this like I did before, saying that this is like the first problem. When we had 5 to the x sine x, it's like that one, but instead of the base being 5, I have the base as e. So I could do that exactly the way I did that problem, and there would be no real changes, other than it's not a product rule up here. It's just term by term. But just watch this and see if you agree that I could do this. If I take natural log on both sides of the equation, why would I want to do that? Yeah, because what happens when you take natural log and e and put them together? It's, you know, you compose them, they go away, and you get whatever was up in the exponent. So it drops that exponent down. If it's natural log of e by itself, it's 1. But if it's natural log of e to a power, this power is what falls out, basically. And technically speaking, this is what we're doing. We have this property of e in natural log. Natural log of e to the x is equal to x. E to the natural log of x is equal to x. So if you put, these are inverse functions. So if you put the e, the exponential function, into the natural log, they undo each other, basically. And you just get whatever you had started with. Here, if you put the x into the natural log and then take e to that power, again, they cancel each other out, and you get x. Cancel not meaning in the sense of like algebraic cancellation. It's through the composition of the functions it cancels. All right, so what we'll have now is natural log y equals just cosine x plus natural log y, x. And now I need to actually find the derivative, right? But I've now said I have natural log of y on the left side. So I can't just do standard derivative. I need to do the implicit differentiation. So I take the derivative of the left and right-hand sides. So derivative of the left side would be what? And be careful. What's the derivative of natural log of y? 1 over y, y prime. 1 over y, y prime. And then the derivative of the right-hand side is pretty straightforward. Negative sine x plus 1 over x. Right? Derivative of cosine is negative sine. Derivative of natural log of x is 1 over x. And then the last thing to do to get y prime by itself would be to do what? get rid of this. How about multiplying both sides by y? Is that okay? So y prime would be y times negative sine x plus 1 over x. And we're almost there. What's y? Yeah, go back up to top. This is what y is, right there. So you get y prime is e to the cosine x plus natural log x times what was here, negative sine x plus 1 over x. Pardon me? You would have to get a common denominator, right? Is that, you saying if you want to put those two together? Yeah, you'd have to introduce, this is like sine x over 1, so you'd have to put x down here and an x up here. So it would turn out to like negative x sine x plus 1 all over x. If you wanted to. You don't have to, though. You could just leave it like that. In retrospect, looking back at this, I kind of think I would have preferred to just do it the way that we did the number 1 part A. Like, what's the derivative of e to anything? Itself, right? So we just would have written this down. And then we would have said, what's the derivative of what's up here? Negative sine x plus 1 over x, and we would have been done, right? All right, so we're gonna flip to 8 to make us. Is this the way you wanted to do things? It's kind of your study group, so I don't want to overtake. Was this the plan? Well, whoever organized this, is this okay? Yeah. Is this the way you want to do it? Yes? All right. Well, I don't want it to turn into like what class is, you know? Because the difference here is that I want you to stop me if you don't get it. So again, I'm not going to tell you use L'Hopital's rule. I'm just going to say on the test, find the limit, right? So this review is more of just to kind of really get your brain in the right place. Hopefully by doing enough of these, when the test comes, you'll know. But I mean, look, this limits, the only problems on the entire test that have limits are all L'Hopital rule problems, right? So I mean, you should know as soon as you see a limit, you're most likely going to be using L'Hopital's rule. Unless I just give you a limit that doesn't need L'Hopital's rule, which, yeah. It's like that Sour Patch commercials. Have you seen those? You know, like the little, it's like I bring you tacos, but then give you a bunch of trick questions. No, I wouldn't do that. All right, so let's talk about what's happening here. You know, you always try just to direct replacement. X is 0, and see what you get. 5 times 0 is 0, so I'm getting a 0 in the top left corner, minus sine of 0, which is again 0, over 0, so I get 0 over 0, and 0 over 0 is what you need to use L'Hopital's rule, right? That or infinity over infinity. Those are the only two ways you can use it. So I'm allowed to apply L'Hopital's rule, so I put my little equals, my L or my H, whatever you prefer, rewrite the limit. So this just lets everyone know that you're using L'Hopital's rule. I was actually looking at a book the other day that was using L'Hopital's rule, and they were not putting this, and I was confused. Why wouldn't they show that? You know, like why wouldn't they let the student know? So a student reading through the work is seeing L'Hopital's rule happening, but no indication that it's happening. I thought that wasn't very nice. But so we want to make sure we're reminding ourselves what we're doing. So L'Hopital's rule says you take the derivative of the top and bottom separately, right? No quotient rule. It's just top and bottom separate. So the derivative of 5x minus sine x, this is two terms. So derivative of 5x is 5. Derivative of sine x is cosine x. Over derivative of x, which is 1. And now we try direct substitution again. Let x go to 0, and what do you get? 5 minus, what's cosine of 0? 1 over 1. This is just 4, isn't it? So since I got an answer, I just plug that in over here. That's my limit. The limit's 4. Any issues there? Part B? Lim x goes to infinity, 3x squared over e to the x. Hey, what's up? It's a review. There's some tacos. Yeah, go ahead. So what's going on here? Okay, so direct substitution, e to the infinity, what is that? Infinity? You understand that, or yes? Okay, that's, when you say e to the infinity, what you really mean is look at the graph of e to the x and go out to the right forever. And what does the graph do? It takes off to infinity, right? It gets bigger and bigger and bigger. So the bottom is infinity. What about the top? Infinity also, right? 3 times infinity squared. Infinity squared is infinite. So we have infinity over infinity. We can apply L'Hopital's rule. So we have L'Hopital. Derivative of the top, 6x. Derivative of the bottom, what's derivative of e to the x? Careful. Just itself. The derivative of e to the x is itself. Two functions you should try and put into the memory banks is derivative of e to the x and derivative of natural log of x. Derivative of e to the x is itself. Derivative of natural log of x is 1 over x. They come up so much further as you keep going that you don't want to be referring to a table or something for that. I just realized I'm not plugged in. Okay, so what's happening here? You go infinity on top and infinity on the bottom. So if you have that again, just apply L'Hopital's rule again. You can apply L'Hopital's rule as many times as you want to, so long as each time you do it, you continue to have the infinity over infinity or 0 over 0. So it is possible to apply L'Hopital's rule, 1,000 times. If that had been like, the original problem would have been 3x to the 1,000th power, right? Then you would have done, first derivative, and then you would have had x to the 999, and the bottom would be e to the x. That would still be infinity over infinity. And then you do it again and again and again. Every time you do a L'Hopital, the power on the top will come down by 1. So you wouldn't have to ever show that, but I think you understand that, hopefully you understand that you could keep applying the rule. Now, yeah, the thing is you can't just keep doing it without looking each time at what you have. All right, that's a danger zone. So this is still infinity over infinity. So we apply it again. Limit x goes to infinity of 6 over e to the x. I'm waiting for my first pre-cal student to walk in here and throw the equilibrium off in this room. Yes. All right, so now what's happening? That's going to 6 over infinity, right? 6 over infinity goes to 0. So now you are not allowed to apply L'Hopital again. Okay, that would be a mistake. So we are done. We can actually say that this goes to, what, a fixed number over infinity, which goes to 0. So the answer here is 0. This is actually a kind of an interesting problem if you think about it. Like if you start plugging in values of x, right? Just look at this right here. If I plug in, let's say 1, I get 3 over e. If I plug in 2, I get, what, 4 times 3 is 12 over e squared, right? And if I plug in 3, I get 9 times 3, I get 27 over e cubed. What we're saying is that if you let x get bigger and bigger and bigger, what happens is that the denominator gets a lot bigger than the numerator gets. And so it eventually squashes down to a very small number. Does that kind of make sense? But didn't I just say that if you let this be x to any power, we could apply L'Hopital over and over and over? So if this was actually 3x to, let's say, the 2 millionth power, what's 2 to the 2 millionth power? I mean, that's off the charts big, right? Way bigger than e squared, yes? But if you let x go to infinity, eventually e to the x gets bigger than that. Because we know that eventually with L'Hopital's rule, we would do like 2 million derivatives and the power would come down each time, and eventually, you know, e to the x just keeps cycling e to the x, e to the x. So if you were to graph these two, right, it would look like the x to the 2 million just took off and e to the x is down there going, okay. But if you go out far enough on the x-axis, eventually e to the x is going to take over. That's how fast e to the x grows. And I can do that for any power of x up here. Just a little side note. E to the x, well, exponential functions are one of the fastest growing functions that are around. The only thing really that much faster than e to the x is the function x to the x. Did we talk about that a little bit? Yeah, I mean, not only is the exponent growing, but the base grows too. So that grows even faster than e to the x does. Okay. You study that in Cal 2 more, things like that. You have a question? Yes. Yeah, fixed over infinity is always 0 because your numerator's staying what it is, and your denominator gets bigger. You know, so if I had like 6 over 1, 6 over 2, 6 over 3. So what's happening to these? They're getting smaller and smaller and smaller. 6 over a million, it's going to 0. So no matter what, if the top is fixed and the bottom's getting huge, that's going to squash down to nothing eventually. I mean, of course, it never reaches 0, right? But it's approaching 0. All right, next one. Well, that's why I'm recording this, and I'm gonna. Oh, hey, how's it going? Good. I have your review. The equilibrium's off now, guys. Oh, you need it. What's that? Okay. All right. You can sit here if you want, or in the back. I'm doing calculus right now, but you just tell me what question you want, and I'll do yours, and we'll switch back and forth. I can get the book. Yeah. Let me put this one up here. X goes to 0. X minus sine x. The answer to that problem is 0. Yes. It's the one I boxed. I think I did box it, right? Yeah, I just box it here. So I mean, this would be fine as far as work on a test, but here are things I'm looking for. You wrote this down. You wrote equals. You put L'Hopital's rule. You continued to write the limit. You wrote the ratio again. You somehow signified you knew what was going on with this. You did the equal sign again, L'Hopital's rule. You wrote the limit again. You wrote it. You told me you knew what happened here and you put 0. Yeah. Yeah, just keep it. I mean, logical train of thought. If you just sit here and on this problem, all you do is say this is 0. I mean, I can't give you any credit for that because I don't know if you guessed. I don't know if you put it into your calculator or graphed it. I don't know what you did, right? That's why I told you about that problem x to the 2 million. Because if you graph that, you're not going to know it goes to 0. Because your window is not going to be big enough to show it. So people always say that, like, well, I could just do that on my calculator. Yes, but I can make up a problem that your calculator can't do. You know, so that's not the point. All right. Y'all think about that for a second. I don't know, is it? So you're getting 0, right? Over 0. Apply L'Hopital's rule. You get what? That is still 0 over 0 because that's 1 minus cosine of 0 is 1 over 3 times 0 is 0. So you get 0 over 0 still. So you can apply L'Hopital. What is the derivative of the top? Positive sine x, yes. Over 6x, 0 over 0, 0 over 0 again. L'Hopital. Cosine x over 6. And now that goes to 1 over 6. Tamikas, did you find what happened there? Yes, you're good. No. Mm-mm. No. Yeah, like a notation to let you know how many times. No, because L'Hopital doesn't care where it came from. Like if I could have started with this right here is the problem, right? I could have said that's the problem we're starting with. L'Hopital doesn't care where that came from, right? L'Hopital is just going to use the property. If it's 0 over 0, you can do this. All right, you all try the next one on your own. See if you can get D. work best with L'Hopital's rule. Let's just see where it goes, all right? So the fact that secant looks like this at pi over 2, secant's the reciprocal of cosine. So if we draw cosine like this, secant does this, and on this side does this, right? That's basically that one part of secant looks like that. And then tangent looks like this at pi over 2. It does this. Comes up like this, and on the other side it goes down like that. Right. That's just a picture. This is tangent. This one is secant. So that gives us infinity over infinity. You don't need a graph. Just don't guess. Yeah, you could say something like, you know, infinity over infinity from graphs or something like that. Which equals, now by L'Hopital's rule, hoping for the best, preparing for the worst, derivative of secant x. Secant x tangent x over derivative of 1 is 0, derivative of tangent is secant squared. Clean it up algebraically first. Cancel a secant. No L'Hopital. You get tangent x over secant x. What does that give you? Same thing, right? Infinity over infinity again. So, shall we try L'Hopital again? Secant squared x over, it's going to be an endless loop, isn't it? This one's going to give us secant x over tangent x. And then the next time we do it, it's going to go back. And do you see we're not going anywhere with L'Hopital? Do y'all see that? So I don't know what you want to write over here. I mean, shit. That's what I would write. I mean, I would be like, I'm not happy about that, right? So there's got to be something else that can get us this, right? No L'Hopital's rule. Yeah, I'm recording. Is that okay? Did I offend anyone here? I'll take that off of there. I mean, that's what I would think. I'm just telling it how it is, right? So let's go back to this. In pre-cal, whenever we ran into an issue where we were having trouble with trig stuff, we always like to turn things in terms of sine and cosine. It just always seemed to make life better if we were ever stuck. Let me just double check it. So you brought that over -1/2. No, positive. And then this one, yes. Good. We don't need that. Okay, so general, no. This is it, general solutions only. So that's all I want. Move on. Okay, so on this one, this looks very much like this one, but you have sine squared and cosine. So it would be nice if they were both what? Okay. So which one would be easier for you to turn? Using? Yes. So do that, and then just do it the same way you did this problem. Get everything to one side. All right. Well, this is what? Just what? Well, you can't reciprocate this yet because you have a plus 1. But I like your idea. How about we put these two together? Common denominator? So I'm not doing any L'Hopital, right? This would turn into cosine x plus sine x over cosine x. Do you all agree? If I just put these two together with a common denominator, now flip it up. You'll know what I'm saying? Flip it up, and what do you get if you flip that up? Cancel the cosines, so what would be left? What is it? See, this cosine x is up here. This cosine x plus sine x is down here. This is gone. These cancel. So you're left with what? 1 over cosine x plus sine x. Yeah? And let x go to pi over 2. Hey. I have one more review. Would you like a review? Did you get it? There's 2 bean and cheese tacos left if you want a bean and cheese taco. Okay. What does this go to? Hold on. Don't say anything. Cosine of pi over 2. Can you tell us what cosine of pi over 2 is real quick? No pressure. You're not going to do it? I'll put you on the spot. All right. X coordinate, cosine pi over 2. 0. Sine of pi over 2, 1. So we get 1. 1 over 1. No L'Hopital, just simplification algebraically. That's all it was. Tricky problem, right? The moral of the story on that problem is that as great as L'Hopital's rule is, there are limitations. I mean, there are things that it can't handle or that can get you stuck in that infinite loop. We are going over, I was asked to do every problem A through F on number 1, and then every one of the number 8 L'Hopital rule problems. That's what we're doing to start, and then after that, we're going to kind of mix things up in here, all right? No? No? I know, it's okay.
So, is that correct? That's correct.
Let me see, hold on. The 4 would go to this one also. The 4 goes here too, because you're rewriting that like, you're replacing sine squared right there with 1 minus cosine squared theta, like that. So the 4 is in front. That's what you had, right? Replacing this with this, and then it would go here and here. 4 minus 4 cosine squared theta. Yeah, just change that.
Yep. So whenever now.
Same thing here.
Should I move this over here?
Do you like negatives in front like that of your squares? Then move them all that way. Doesn't matter which side they're on.
If I move this over here, it's gonna be 4 plus 4.
No. If you move this one over here, it'll be 4 cosine squared theta, and then if you move that one over here, it's gonna be minus 4. So you're subtracting 4 both sides here. You're adding this both sides there.
Okay, so.
Are y'all trying the next one? Okay.
So it should be
like. There you go. Yep. And then put equals 0 over here, because you moved everything off that side.
I can't put the equal 0.
Sure, you could. Yep. Now combine things together. Yeah. Yeah. 1 minus 4, right? Do 1 minus 4. And put it in descending order. So put it like in the order like cosine squared first, then your cosine, then your number. Did y'all get E yet? That's what it's going to start as, right? Do you have an answer? No? Yeah, you want to. So with L'Hopital's rule here, well, we got infinity over infinity, right? Does everyone agree with that? Let x go to infinity. Natural law goes to infinity. So L'Hopital, one over x on top. X to the negative 1/2 what? Well, the 2 would cancel. Yeah. Yes. Now, I'm going to write it slightly different. I'm going to write it as 2 times 1 over 2 root x. I'm just going to write it that way because that's the way I've always done derivatives of square roots. I've always said it's 1 over 2 root x, but we had a 2 out here already. Is that okay with everyone? Sure? Cancel the 2's. So we have limit x goes to infinity. Do this part? Okay, 2 is just a constant attached to a function, so it's just going to come down. The derivative of the square root of x is always going to be 1 over 2 root x. Now, the reason why is because square root of x is really x to the 1/2, right? Then doing the power rule, you bring the 1/2 out. X subtract 1, you get negative 1/2. This is the same as 1/2 times 1 over x to the positive 1/2. But x to the positive 1/2 is the same as square root of x, which means just 1 over 2 root x. So instead of going through all that mess, I just remember it because it happens so much that I just always put it there. Is that okay? So what does that equal here? 1 over x over 1 over root x. Yes. And you can flip. Are you having trouble factoring that? No, you're good. Okay. You can flip this and get root x over x. Right, you're taking 1 over x, you're dividing by this, so you multiply by the reciprocal. Now, this is a big question for you here. Can I apply L'Hopital's rule right now? Should I apply L'Hopital's rule right now? You have infinity over infinity, but the thing is you haven't algebraically simplified this thing yet. The square root of x divided by x simplifies, right? So you should not apply L'Hopital's rule right now until you've simplified this. Yes. Yes, square root of x over x is the same as x to the 1/2 over x to the first power, which by properties of exponents is x to the 1/2 minus 1, right? X to the n over x to the m is equal to x to the n minus m. What's 1 minus 1/2? Negative 1/2. Now, so that's what this turns into, right? But I'm not going to write it as x to the negative 1/2. I'm going to write it as 1 over the square root of x. Now, why am I going to write it that way? That's this rewritten, right? I want to be able to see very easily what happens. I can tell very, very easily what's going to happen here. I'm going to separate this. This over here is a different thought than this. Questions? You got it? You sure? It's your time. This is your time. Okay. What happens here? That goes to 0. It's fixed over infinity. That goes to 0. Question? You're good? What's that? Okay, you're not good. F. Okay, look, and so I'll just tell you right now, parts A through E on number 8 were all 0 over 0 or infinity over infinity. All of those were, right? From here on out, they're going to be different, all right? So I guess what I'm saying is A through E, it was pretty much, you would almost automatically go to L'Hopital's rule because you had the form you needed. Starting with F, things change. What form do we have here? So where are things going? That's infinity. That's headed towards infinity. X is headed towards infinity times sine of 1 over infinity, which is 0, right? Fixed over infinity is 0. So you have sine of 0 is 0. So you have something, one of your factors, x, is trying to get huge. This other factor, sine of 1 over x, is trying to get very small. You're multiplying them. Who wins? You don't know. So this is an indeterminate form. Now, whenever we have infinity times 0 or 0 times infinity, we always do the same thing. We grab one of them and we drop it into the denominator. In other words, we write it as it's reciprocal on the bottom. So I always like to grab the one that's like easier, that looks nicer, like x, and I'm going to put it on the bottom. So I'm going to, and there's no, we don't need to tell anyone that we're doing this, like represent it somehow with a symbol. We just do it because it's just algebra. It's not a very natural algebra thing, right? We usually, when we're using algebra, we're trying to clean things up, right? We're trying to make things look better. This is an example where we're actually trying to make it look worse so that it gives us the form of something over something instead. Y'all see that? X is the same as 1 over x down here? You sure? Okay. That's right. So now focus all your attention on this piece right here. Where does sine of 1 over x go? 0. Now, where does 1 over x go? 0. See, what we've done is we've taken something that used to look like infinity times 0. We've turned it into something that looks like 0 over 0. Because if we have something like that, we can use L'Hopital's rule on that. You will always do that when you have infinity times 0. I should say you will always try that. Okay, go ahead. See if you can get that. You have to take a derivative top and bottom now. How'd it go? Pardon me? Yes, it is. Let me see. I don't remember how this thing factors. Excellent.
Okay, so on this one, do I do like, do I move that here?
If you want to.
And then, like, my 2?
Can't do that.
You can't do that?
Mm-mm. Because the 2 is trapped inside the tangent. It's stuck there. It's very difficult to get that out of there.
Well, like, I thought it was.
Continue to think factoring. Continue to think factoring right now. You have something squared minus 1. Right? So you could factor that?
Yeah, I think.
Yes. Try it. Well, write down over here. Write down x squared minus 1. Just over on the side over there.
Okay, wait, what?
X squared minus 1. Can you factor that?
Yeah.
Remember difference of squares?
Yeah,
Yeah. Remember that?
but I didn't want to say it because I thought it was confusing.
So you want to do that with that.
So it should be like.
Mhm. Mhm. Each in parentheses, right? Now, since you have two things that multiply to be 0, right? Just like you did back here, you had your two things, you just set them both equal to 0. So set the first one to 0, set the second one to 0, and then I'll help you with that if you get stuck with that. But you're almost ready to go to the unit circle and start looking at where tangent is. Are y'all getting it? No? I'll come around. Did you get? Is it ugly? Does it keep getting uglier? No, that's it. Mhm. Mhm. Chain rule. Yep. Yep. Okay. So what happened here? Did you get a derivative there? And they canceled? Excellent. Now what happens is x goes to infinity. Are you working on chain rule? Okay. If okay, let me show you. If I were doing 1 over x, I'd rewrite as x to the negative 1, and then I'd do the derivative of this, which is power rule. So negative 1 will come out. X to the, now we subtract 1, negative 2, which would give you your, drop it back down, negative 1 times 1 over x squared, which is negative 1 over x squared. But again, that's one of those ones that happens so much that it becomes automatic eventually. Yeah. Yeah, the negative is going to be there. But the good thing is the same thing's going to happen on the top one, right? When you do the derivative of what's in there, and they're going to be exactly the same and they cancel. So you got, what is it? 1? 1? Yeah. The exact same thing, yeah. Yeah, it's almost, you can almost see it right here, that you know that when you take the derivative, you know that these are the same, so eventually those parts of the derivative are going to cancel. But you have to get through the chain rule. Did you get it now? Yes? No. Can't take that 2 out of there. What you're saying is tangent, right, of something is equal to what, negative 1? Is that the one you're doing first? Okay, go to your circle. Tell me where tangent's negative 1. What angle is tangent negative 1? No. But since you're requesting them to make us, I'll make sure that I throw a couple on there for you. Why is that not going away? All right. So everyone got this one okay? All right. Have you tried the next one? You're waiting on me, huh? Don't wait on me. Yeah, that's only because I have to put the plus there because natural log is not defined for negative values and square root of x isn't either. So it's just to make sure it makes sense, that's all. Did you figure out where it is? Mm-hmm. Awesome. Good. Yes. See, you've got that. You've got that.
I was looking over here and I was like, what the hell? Like, what did
Yeah.
I do? And then I was like, I took the sign.
Mm-hmm. That's right. Yep. Yeah, so you can't get the 2 out of here until after you've come up with your angle.
I guess I was confused because I thought, like, okay, I know what tangent 1 is, but I don't know what tangent 2 theta.
Gives you -1, yeah.
Yeah, I don't know.
Okay.
Confusing, but I get it.
Yes. That's 0 over 0, though. That's not what we did. No, we did not. When we got here, okay, right here, we flipped the fraction because these are both powers of x. So I flipped it and made it this, and then went over here and figured out what that was algebraically. Square root of x over x is this, which is this, which is this. So you subtract the powers. And then I rewrote that, x to the -1/2 is this. And now it's fixed over infinity, which goes to 0. Got it? Got the other one?
Is that how you write it? Ooh. I don't know.
Mm-hmm.
Oh, it is?
Mm-hmm.
Okay. And then, yeah, I'll
Get the other one. It's going to be the 4 corners, right? That's what you're basically getting. When they're all said and done, it's these give you tangent is -1 here, and then +1 are the other corners. What are you all getting here when you plug in 0? Well, try and plug 0 in, just like we did. Okay, so go to the graph. Well, you can plug 0 into the square root. Square root of 0 is 0. So that's going to 0, and then -infinity. Now, where are you getting that from? The fact that the graph of natural log. Remember I said I wanted to give you all a quiz on the graph of natural log of x? Because everyone kept on forgetting what it's doing as you go to 0. The natural log of x, as you go to 0, as you approach it from the right-hand side, dives down to -infinity, right? So we get this term here, this factor, sorry, goes to 0. The other one goes to -infinity. And so that's an indeterminate form. So you have to convert it. To convert it, we're going to do what we did in the previous problem. Which one do you want to drop down? One over, well, if we have 2 choices. We can do this. We can leave the natural log there, and we can turn this one into this, right? Or we could have done, leave the root up there, but then do this here, right? Which one do you prefer? The left one. Now, here's why. The derivative of natural log of x is simple, 1 over x. Derivative of 1 over the root x, I could rewrite 1 over root x as x to the -1/2 and do power rule. Look over here. Derivative of square root of x is easy. I concede that is. But 1 over natural log of x, that's a quotient rule. You'd have to do a quotient rule. We can't just take this is not just 1 over x. That's not the derivative of that. Because it's a quotient, right? Do y'all see the difference? So go ahead and do your L'Hopital on this here. See what you get. Anyone get it yet? No? Let me know when someone's got it. Now, I was going to say I can't wait for you to try the next one. To how? No. How though? Do you see that the issue you have here is that part of your problem has 2 thetas in it, the other one has just theta?
Yeah.
Wouldn't it be real nice if they were all theta?
Yeah.
So do we have a formula that turns sine 2 theta into stuff with just thetas instead?
Yeah.
Where? Yes. So turn that left side into this, and then think factoring at that point, okay? You got it. You've got this one. You can get it. Look at one. No, it's not an identity. Those won't come until the other side where it says verify, verify, verify.
So that means I'm still doing it, like I'm looking at both sides?
Yes. So you can move everything to one side if you'd like. Probably a good idea. Did y'all get this for your derivative? Derivative of natural log of x is 1 over x. Derivative of 1 over root x is this. Where did that come from? Or did y'all do quotient rule on that? This is the same as x to the negative 1/2, isn't it? That's what this means? X to the negative 1/2? Yay, nay? Yes? Okay, what's the derivative of that? Power rule. Negative 1/2 comes out. X to the, take 1 away from a negative half. Negative 1/2 take away 1 is negative 3/2. Do y'all see where I'm getting this from? Now this looks like a big mess, but I'm not too discouraged because they're all powers of x, right? So I should be able to clean this up. I'm not doing L'Hopital. X is approaching 0 from the right. Negative 2 times x to the negative 1 over x to the negative 3/2. So what have I done here? Negative 1/2. I just flipped that back up as a number, right? Since it's in the denominator, I can just flip that up as a negative 2. And then I rewrote 1 over x as x to the negative 1. I just put the x to negative 3/2 here. And now what I'm going to do is I'm going to use properties of exponents on this. So I subtract, right? It's going to be x to negative 1. Take away what? Careful here. Negative 3/2, which is the same as x to negative 1 plus 3/2, which is what? X to the half. What's x to the half? Square root of x. So this becomes limit x approaches 0 from the right of negative 2 square root of x. And where does that go? Let x go to 0. 0. I also realized just now you might have just done this instead. Like if you have a negative exponent, you can bring it up. If it's a negative, you can bring it down. Just flip those over and then do the same thing that I did here. You still get the same answer. Yay, nay? Any problems with that? Okay. What's wrong? Switch which part of this? Here to here? Or just from here to here? Okay, so 1 over x is the same as 1 over x to the first power, which I can rewrite that as x to the negative 1. Because remember, negative exponents mean you can drop it to the bottom. So I'm just rewriting this so that it doesn't look like a fraction. It looks like just x to a power. So that's this. Yes? And then this was the derivative. Were you okay with that? That was the derivative. Yes? Okay, so, and then this negative 1/2, I don't really care. It's right here. Just flipping it back up. Flipping it back up makes sense? 1 over negative 1/2. Yes? And then here, just property of exponents, use the rule. The rule I'm using is x to the n over x to the m, x to the n minus m. That's the property of exponents. So x to the n over x to the m is x to the n minus m. Do the, just do this little addition, and then you get that, and then I just rewrite that back here. Anybody else? No? Sure? Oh, this next one's good. Are you stuck? I know. I said it. It's good because I can't wait to show you. But I want to see if anyone does anything with it first. We'll see if anyone has an instinct of what to do. It's just a number in front.
I know, but does that mean it would be like?
So I said think factoring, right?
Yeah, so does that mean it's like -2 root 2? Like, to do the thing, and that sort of thing?
You would have to have cosine squared for that to work. Okay, so in factoring, the first technique of factoring, do you remember what, like, the first thing we ever learned factoring is? Mm-hmm. What do those both have in common? Mm-hmm. Cosine theta, right? That's it. So pull the cosine theta out, and then what's left there? Mm-hmm. Equals 0. 0. Just rewrite the equation. Okay. That would be that first one. That would be that one. Good. Perfect. Now, set those both to 0. Set it to 0. It'll work out nice. What's happening here? 0. Fixed over 0 is going to be infinite. Fixed over 0 is going to be infinite. Fixed over infinity is 0, but fixed over 0 is infinite. That's right. That's it. But you have to first establish the fact that you have a problem, okay? The problem is that this one right here, 1 over 0, 1 over 0. So you have 1 over 0 minus 1 over 0. It's basically undefined, and it's all screwed up. So you get a common denominator. Common denominator between both of the fractions would give you x minus sine x over what? X sine x. So could you put those two together with a common denominator? Okay. Okay. Well, you get 0 over 0 now, don't you? Don't do that. Don't go back there. Don't hit the reset button. Right? 0 over 0, we don't know. Right? Infinity over infinity, we don't know. That's what L'Hopital's rule is for. It's for that case. So if on the test you get to a problem like this and you get 0 over 0 and you put 0 or something like that, I'm probably going to just a little tear is going to come out of the corner of my eye, just a little bit. And because I'm going to know you're capable of this, but so I'll shed a tear for you. I'll be so sad for you. All right, L'Hopital? Okay. Derivative of x, 1. Derivative of sine is cosine over, product rule. It's a product rule, right? This is a product. Now, L'Hopital allows you to split it up and do top and bottom separately, but if the bottom is a product, you've got to do product. Like, you can't get around that. So I've got to treat this bottom as a product rule. So what is the derivative of x sine x? It's 1 times sine x plus cosine x times x. Derivative of the first one, 1 times the second, plus derivative of the second one, cosine, times the first. I believe at this point, I think good things happen. Let's see. What happens if I plug 0 into the top? What do I get? 1 minus cosine of 0 is 1. So you get 1 minus 1 on top over. Here we have sine of 0, which is 0. And then plus, oh crap, I thought we were okay. Never mind, sorry. Cosine of 0 is what? 1, but then times 0. So we get 0. So we're still screwed. So we got to do L'Hopital again, maybe? Don't be afraid.
I forgot.
You got the other one?
This is like cosine, but oh yeah, I got that.
Okay.
Yeah.
Well, I'll look. Cosine 0 at pi over 2 plus pi k. Root 2 over 2 sine is your y coordinate there and there. Okay, you're good. Excellent.
So this I can get secant.
This one's hard.
Right? Then I can begin the process. But
Are your notes in here or are they over there?
this is like.
Is that from class?
Yeah.
Can I see that? I think I have a problem in there that I did.
Also, like, it depends on
It's mixed up.
yeah, this is like 2 weeks ago.
Okay, let me look through this for a second and see if I can find something in here. Yeah, it's not in here.
Is it too if it's too much forward?
Oh, wait a minute. Oh, so this goes backwards?
Yeah, this is towards the beginning of class.
Oh, this. Oh, yeah. No, I don't want to go. I don't want to go that far back. Yeah. Okay. So let me see. Ah, here we go. This is close to what it is. Let me see if I. Ooh. There we go. This is it right here. So you have secant instead, right? And you have secant is 4, and inside you have 2 theta, right? That's your problem.
Oh yeah.
Right. Right. So it's very similar to this one.
Yeah.
Okay. So let's see what I did here. First, rewrote secant, cosecant, as 1 over sine.
That's what I was thinking.
Okay.
I was gonna do that, but I was like, I
Okay.
thought you said something like if theta has a number in front,
Yeah.
you can't do.
Try that. Write it. Now, what is secant? It's not 1 over sine. Oh, what happened? Did y'all do a derivative again? Is it an endless loop? So on the bottom, what did you do? Derivative of the top is what? Sine x? And then on the bottom, you did derivative of sine x, which was cosine x. And then what did you do here? Product rule? Yes? You did product rule here? So you get negative sine x times x. That's times. So derivative of this times this plus derivative of this times this, which is cosine x. Is that what you had? So this is limit x goes to 0, sine x over, you put that as what? 2 cosine x minus x sine x? Now let x go to 0. rare breeds. Really? We're right-brained. So divide by 4. Does that make sense, everyone? It's a bit involved there, huh? But it's 2 product rules in the L'Hopital, but it worked out eventually. You're going to need help with that.
No, I'm not going to.
No? Okay. All right. How about I? All right, so remember I said A through E was infinity over infinity or 0 over 0. F, G, and A, well, F and G were 0 times infinity, right? F and G. H was infinity minus infinity. I and K are 2 different types of forms, as we're about to see. So this one is the base wants to become infinite, right? But the exponent wants to become 1 over infinity is 0, right? This is an indeterminate form. The base wants to become huge. The exponent wants to turn everything into a 1, right? Because anything to the 0 should be 1. So who wins? We don't know. Anybody remember how we did this one? What we did is we called this limit y. So I'm doing this anytime I see this. What did we do when we saw 0 times infinity or infinity times 0? What did we do? We grabbed one of them and pulled it down, right? When we see infinity to the 0, or like on the next one, part K, as we'll see, if we see this, what we do is we always set it up as an equation, and then we take the natural log on both sides. And the reason why we do it is because, why? I'll be able to take this 1 over x and pull it out front. So I'm going to write down, now be careful with this. I'm taking the natural log on both sides. Let me do it in a different color. But what was over here on the right side that I'm taking the natural log of? What was over here? ln x to the 1 over x. Now, quick question. Why could I not pull this 1 over x out right now? I mean, there's a natural log there right now. Why can't I pull that out? Yeah, but without anything being over here, I mean, like, why is it that I can't just sit here and pull 1 over x out in front of this log? It's because these parentheses. This 1 over x is acting on the entire natural log, isn't it? As opposed to what the formula says. The formula says if you have natural log of x to the n, then you can pull the power out. But what's that n acting on? Just the x, not the whole natural log. So I can't pull this 1 over x out because of this natural log. I can't do it because the 1 over x is not acting just on the x. Do y'all see the difference? But if I come in with natural log on both sides, now I have natural log of something, right? And that something is being raised to the 1 over x, so the 1 over x can come out. So I've got 2 natural logs here. It looks weird, but that's the way it's going to be, all right? So I've got natural log y equals limit x goes to infinity. The 1 over x came out times I have natural log of x. Okay. You have your calculator out, though. You just take that out? Good. You need it. You'll need it for this. Pardon? Well, tell me what this limit's doing, all right? What does 1 over infinity go to? Okay, what's natural log of infinity? That goes to infinity. So I'm basically plugging infinity into natural log again. Natural log of infinity is infinity. So this looks like a 0 times infinity. So now we're back to what we were doing in the previous two problems or three problems, right? So you got to pick one and drop it down. I think the natural one to pop down is this one. What will 1 over x look like when I drop it down? Just x. Because it's going to turn into 1 over x, which is just x. I guess the point I should make here is that you could have just done this. You could have just done that to start out. Like that 1 over x out in front was really this, wasn't it? Yeah, I mean, you'd multiply straight across. So this right here gives me infinity on top and infinity on the bottom right now. But I wanted to leave the 1 over x out there just so you could see that it does turn into this form. And that's the whole point of this. When we come in with natural log on both sides and we do this, you should always turn that form that we had up here, should always turn into something like this. Mm-hmm. Yeah. So I'm rewriting this, preparing it for L'Hopital's rule. Now that's infinity over infinity. And yeah, derivative top and bottom separately. I like the derivative of the bottom, don't you? Yes. So here's my indication that I'm using L'Hopital's rule. I'm just putting it in between the equal sign there. Notice I've carried the natural log y down the whole time. I'm doing that because at the end I'm going to need to switch back to what y is, not natural log y. So I'm bringing it with me the whole time. Okay, so you said derivative of natural log of u, right, of something is 1 over itself, or 1 over that something. So 1 over times 1 over x. So the derivative of what was inside is the derivative of natural log, which is 1 over x, right? Then times 1, which you don't necessarily need. So that's the derivative of the top. Over, all over 1. Let x go to infinity. 1 over infinity, which is 0, times 1 over infinity, which is 0, right? 0 times 0 is 0, divided by 1 is 0. So this limit is 0. 0 divided by 1 is okay. Right, so this looked like 0 divided by 1. And now we want to get it back to y. So how do I undo a natural log? Come in with e. So e to natural log y. Whatever I do to that side, I must do this side. In other words, I use the exponential operation on both sides of the equation. I shouldn't even say that. It's just bad, but it's using inverse properties. I don't want to get too technical, and I just don't want to come here and say, when you do e on both sides of an equation, it's not like multiplying both sides of an equation by 2. It's not the same thing, because e, you're not multiplying both sides by e, right? It's like you're taking e on both sides. It's a different operation. So let's not get too caught up into it right now. I don't want to spend time on it. But what does this turn into? Y equals e to the 0. What's e to the 0? 1. Right? Anything to the 0 is 1. So our answer all the way back up here was 1. Did you get it? You think so? Okay. Okay. All right, you want to try K? Last one for L'Hopital. Let me continue this now. Did you get it or not? You're getting there? Okay, so what was the form you had? One to the infinity, right? Right? Well, because what is 1 over, what's 1 over 0? It's infinite. Yes. Well, it is undefined, but just think about the graph of something like 1 over x. 1 over x, the graph looks like this. What's happening as you approach 0? It goes to infinity. So anytime you have fixed over 0, you're always going to have some asymptote there. So this is divergence going to infinity. Now, what? Hold on a second. Well, it's a little more complicated than that. Yeah, because look, damn it, I didn't want it to do this. Okay, I'm approaching 1, right? And I'm approaching 1 from the right side. So values like 1.0001 would be something close. Yes? Yes, so I would be like that exponent would be, it would be 1.0001 raised to the 1 over 1 minus 1.0001, right? Well, check this out. 1 divided by this is a very small positive or negative number. It's a very small negative number, right? Which means that this is approaching a very large negative number. Do you agree with that? A very large negative number? Right. This is a positive divided by a negative, yes? It's a negative number. But because the bottom's getting small, it's getting huge. So this is going to be a huge negative number. Agreed? So what would happen if I take this number like 1.0001 and raise it to a huge negative number? Well, what does negative mean? 1 over it, right? 1 over it. Do y'all follow me? So this is 1 over 1.0001 raised to a huge number, but not negative anymore, right? And what is 1.001 raised to a huge negative number? We don't know. We still don't know. Okay, sorry, I'm thinking out loud here because it's a little more. There's a little more involved here than just, oh yeah, it's going to infinity, right? Because I still don't know what this goes to. What if this went to infinity down here? The whole thing would go to 0 and I'd be done. But I still don't know what this does. Okay, so sorry, this is me thinking out loud. Let's continue and do what you did, all right, which was we looked at this as 1 over infinity, and now you come in with, called the thing y. It was limit x goes to 1 from the right of x to the 1 over 1 minus x. You took natural log on both sides. And when you did that, that 1 over 1 minus x came down, and then you put it down on the bottom, didn't you? So everyone's okay with that? And now when you let x go to 1, what's natural log of 1? 0. 1 minus 1 is 0. So you get 0 over 0 as desired. And now you do L'Hopital. 1 over x over negative 1. And now let x go to 1, and what do you get? Negative 1. This whole thing's negative 1. So you get natural log of y equals negative 1. And now switch your y back to, switch natural log y back to y, and you get what? Y equals e to the negative 1. That's your answer. Just leave it as e to the negative 1. E to the negative 1 is the same as 1 over e, isn't it? So your answer is 1 over e. Yeah, I accept these. I don't mind if you put the decimal, but would you have written this somewhere on the test also? Okay, as long as you wrote e to the negative 1, I'd be happy. All right, so we're what, like almost 2.5 hours in to this? Well, we got a late start. We're a little over 2 hours in. We've finished number 1 and number 8. So why don't y'all look through the rest of this and tell me what you would like for me to do next. Mean value. So why don't as groups, table, whatever, y'all each come up with a problem that you want to see, and I'll just go around and do those. All right? How are you doing here? Are you stuck on the next one?
I don't know if I'm stuck. I'm just kind of trying to
Okay.
make sure I understand.
We did that yesterday.
Yeah.
Okay.
And that's why I was like, why? Like it goes from something.
Yeah. Solving to now finding exact value.
Yeah. So basically, like I'm gonna do sine u.
Well, it's cosine.
But
Oh, yeah, I see. Which one are you gonna use?
this one. Wait, no. Hold on. Oh, okay. I could do any of these.
This is the one that we did, right?
Yeah, that one was because it's sine. You could do. Wait, no. I'm sorry. I'm just.
There you go.
Yeah.
There you go. Okay. So
Okay.
now you're in the right place. Yeah.
Cosine theta. Oh wait, no. Cosine u. This could be u. This could be v.
Yes.
And then like when you're finding the inverse sine of 1/2, is that like just finding?
That's where you cut it off, though. Because it's inverse sine on here, that's where we cut.
You do the restrictions.
Yes.
So if it's like here,
Yeah. What's that angle?
5 or 6.
Yes.
Wait, doesn't that happen somewhere else too?
Where sine is 1/2? It's on the other side, but in a quadrant where you can't be there.
Yeah. Wait, isn't? I thought that was.
That's for sine. That's for cosine. Sorry, that's for sine inverse. That's for cosine inverse. Y'all ready? Okay, give me your first pick. Number 7, the box. I'm going to ask you an optimization question because we covered it last class. I just one example, and I'll try and keep it relatively simple. This would be considered relatively simple. So you'll have an, I know it looks weird because we haven't done one, but let's just work through it, okay? Number 7, the word problem. A box is to be made as shown. if the depth is 3, that's supposed to say 3 times the width, and the volume must be 108 cubic feet, find the dimensions which give the minimum surface area. So what we talked about in class was determining something called the objective function. Do you all remember that? The objective function is the thing that you want to find the maximum or minimum of. In this case, we want to find the minimum, right? What is the objective function? What are we trying to find the minimum of in this problem? Surface area. So the objective function is our surface area formula for this thing. Okay, I'll get to what that is in a second. The constraint equation here is that we have to have a fixed volume. The volume of this thing must stay at 108 cubic feet, right? Our objective is to find the minimum surface area. We want the minimum surface area constrained to having a box that has a volume of 108. Understand? So we need to come up with formulas for both surface area and volume. So our picture, which you were probably very impressed with that picture. It is pretty good. No, it's actually not that great, but okay. Okay, so what is it that I know about this box? Yes, I know that the depth, D, could be 3W. Now, I'm going to use X's and Y's, only because everything we've done pretty much has always been X and Y. So if I call the width of this X, then the depth would be 3X, right? And the height of it, I don't know. It's not really connected to X and Y yet. It's just some height, which I'm going to call Y. Y'all okay with that? So tell me, if you could, what the volume of this is in terms of X and Y. Volume of a box is what? Length times width times height? Or in this case, width times depth times height? It's just the product of the 3 sides. Do y'all agree with that? Okay, that would be assumed that you were okay with that formula. But for us, that's what? X times 3x times y, which I'll just write as 3x squared y. Is that all right? But what must that be equal to? The volume in this problem has to be 108, right? This has to be 108. All right, this right here is my constraint. Whatever I pick x and y to be, when I multiply 3 times x squared times y, I better get 108. Now, let's talk surface area. Surface area is the area on the outside of the box, which is the area of each face of the box. So what's the area of this front face? It's how wide it is times how tall it is, right? So that's xy, but I have one in the back also. So 2xy, so watch, here's my surface area formula. I'm going to call it A instead of SA, A for area. You said it was going to be 2 of those xy's. What else do I have? How about this side right here? What's that? 3x times y. But then I have another one on the other side, don't I? So 6xy. Sorry. Yeah, right? It's 3 times x times y gives us the area of this. But then the one on the other side, double it, right? So 6xy's. Double it, not square it, right? We're adding them together. Y'all look confused. xy plus xy plus 3xy plus 3xy plus, what about the top here? x, that's how wide it is, x, and then how long it is 3x, right? So x times 3x is what? X times 3x is 3x squared, but you're already doubling it, aren't you? Okay. I'm doing this to just show you, I mean, we have two of these, we have two of these, we have two of these, right? Top, bottom, well, I should say front, back, left side, right side, top and bottom, yes? Okay, so 3x is coming from this. This right here is 3x, isn't it? And then how tall is that piece? Oh, you, like where did the 3x come from? Oh, I'm sorry. It says it in the problem, right? The depth. Yeah, if you miss that, it's going to be, you can't turn that into a 3x and you don't have anything. Yeah. Okay, so that was the top and bottom, right? You got it? 3x times that. All right. So let's put this all together. Our area is, how many xy's do we have? And then another 3 and 3, so is that 8 xy's? We have 8 xy's there? And how many x squareds? 6 of them. This is our objective function. Now the problem with this objective function is that it has both x's and y's in it. I'd like to get rid of the x's and the y's and just make it all x's or all y's. But I come back up to my constraint and I realize that I could solve this constraint equation for y, couldn't I? So go ahead and do that. Take your constraint, solve it for y. Y would be equal to, what's 108 divided by 3? 36, right? And then you have to divide by the x squared also. So 36x squared. 36 over x squared is what y is equal to here. Understand? Divide both sides by 3, divide both sides by x squared. So what I'll do now is I'll rewrite this as 8x times 36 over x squared plus 6x squared. So my area is now a function of only one variable. It is 8 times 36, which is 272, is that right? 8 times 36? Wow, am I that far off? 240, oh, plus 48, yeah. 288 over what? X plus 6x squared. And that is that's my objective function written as a function. It's a function of one variable now. Understand? What's the domain of that function? Is there a restriction that you can give me on x? So come up here to this. Can you tell me x can't be a certain value? It might be obvious from this right here. X can't be 0, right? X can't be negative. So what I know is that x must be at least greater than 0. As soon as I see that, I can almost guarantee you now, this is not a closed interval, right? So I'm going to say x is between here and here. I don't even care anymore. I've got to go to the open interval method. Think about it. You can make this a very, very, very long box, right? Just wouldn't be very tall. So there's no limit on what x can be. Yes? Well, no, because it's a volume. Here's the thing. What if I had this thing was 3,000 feet long, right? By what, 1,000 feet? So it'd be 1,000 feet one direction, then the other direction would be 3,000. Well, then what? That's a huge number, right? But I can make it as tall as I want. So I make the height like some little decimal. And so it would multiply to be 108. So it's possible to do it. No, you would never want to do that, but I'm just saying, theoretically, there's no restriction on X. But I'm okay with that. Just keep going with it, right? So what's the method to find max and mins if you're on an open interval? You want to find that change where you go from increase to, well, minimum. We want to go see where this thing goes down, then back up, right? So you need derivative. So take your derivative, find the critical number, set it to 0, right? All that stuff. Come up with your little chart that shows up, down, and you should be able to get it. I'll let you work that. You don't know what? There's only one issue I see so far, and that's, remember on the cosine formula, if there's a minus in there, in the formula it's a plus.
Wait,
Do you remember?
I thought you said, okay, so it's a minus, right? And
Yep.
You said do the one on the top.
No, I said,
You said do the one on the bottom?
Oh. No, it goes straight across. So like if you're on the top, you do the top one here. If you're on the bottom, you do the bottom one here. So it's okay, because all that does is change that to a plus. So change that plus. Plus, that one plus. And then that one. But let me check everything else. You had sine of 1/2 was pi over 6. Cosine inverse of 3/5. Ah, okay. You drew a picture. Good. 3/5. Cosine the first quadrant. Good. And so cosine of 3/5. Cosine. This should just be 3/5, yes. Sine, this should be 4/5. 4/5, not 5/4. Sine is opposite over hypotenuse. Yeah.
What is it?
Opposite SOHCAHTOA. SOHCAHTOA.
H?
Opposite over hypotenuse.
Okay.
So now you'll have the same denominator, which is going to be great.
Like that.
And you can leave it like that. Your next line that you write right there, when you do the plus, what is it, 4 over 10?
Yeah, like that.
That's fine. Good.
Should I add these?
You can't.
I can't?
Well, on the calculator, but you don't need that. Just leave it as an exact answer. In fact, I think I asked for exact answer, don't I? Yeah. How do you mean?
Well, why can't you do 3 plus 4?
Because it's the 4's not under that root with it.
Oh, it's not?
No, it's by itself.
Oh, okay.
Yeah, it's, well, you get it. It's out here, right? The 4's out here. If it were like that, you could, but it's not. I bet you do. Hey, you're like almost halfway, well, never mind. There's a lot here. This is all like verifying identities.
Like, all of these things should be on
Well, I can't make it this long, but I mean, like, this should give you an idea that you're going to have to solve a trig equation, right?
Like, okay. These are just examples of simplifying practice.
Yeah. So there's a difference here. We've got simplify, verify, two different things. Simplify just means there's not an equation, you just start messing around with it. Like, no, that's this. This one right here is your left-hand side, right-hand side thing.
So this one's like just kind of
like,
change it to look different.
Yep. Like, what is tangent squared x plus 1? Well, tangent squared x plus 1 is secant squared. So you can make that 1 over secant squared. And then
Tangent squared, but it has a theta thing on it. Oh, so x and u could be
interchanged, yep. So this is the same as secant squared x. That's the same as secant squared x on the bottom. So that top, it's 1 over secant squared x. That's what you have there. That's really what it is. But remember, 1 over secant is cosine. So that's just cosine squared x.
And it's squared because the secant.
That's right. That's what the first 6 are like. Just simplify.
How would you simplify that?
It says simplify this by first letting x be 2 secant theta. So plug 2 secant theta in there and square it. Try it. Write it down. See if you can figure that one out. Or go to number 7, whatever you think. It's a lot, I know. Y'all done yet? What's wrong? Is that your derivative? So y'all asked me already, right, about the derivative of 1 over x is being negative 1 over x squared. So the 288 in front is just a constant. So I'm ignoring the 288, and I'm just doing derivative 1 over x, which is negative 1 over x squared. Tamika's? What did you do? Quotient rule or something? Okay. That's not what I did, so just ignore me for a second, or pay attention. I'm writing 288 over x as 288 times 1 over x. Tamika's? Is this, right? If you have a constant times a function, you take the derivative, the constant stays, derivative of the function is negative 1 over x squared. So derivative of this and then put them back together. And that's negative 288 over x squared. That's the easiest way to do it. I mean, it's much easier than quotient rule. Quotient rule gets you the same thing. And then the other one was okay, right? Derivative of 6x squared. All right. now set it to 0, right? So we set the derivative equal to 0. Common denominator. So you multiply top and bottom of this one on the right by x squared. Yeah. You get negative 288 over x squared plus 12x cubed over x squared equals 0. Put them together, right? And then once you put them together, you just set the top to 0. You don't have to worry about the bottom, right? So negative 288 plus 12x cubed over x squared equals 0 means all you really have to do is set 288 plus 12x cubed equal to 0, which is, that's where you stop. Well, you're just going to get your calculator out, or just leave it as an exact answer. I'll leave it as an exact answer. Did you what? And just got a decimal? Okay, so I would have been on the next line, I would have had 12x cubed equals 288. And that was 24. I totally made this problem up. I can't believe all these numbers are working out so nice. And then take the cube root on both sides. And you got approximately what, 2.9? The exact answer is cube root of 24, though. All right. Now I have to see if the derivative is ever undefined. Is the derivative undefined or does not exist anywhere? Well, at x equals 0, right? But x is 0 isn't even in our domain, is it? So when I draw my number line, try and draw a little straighter than that. Wow. Can't draw a straight line. I'm going to have the cube root of 24 here. I could put 0, but remember, 0 does not exist to the left of it anyway. It's not domain 0, right? X being negative doesn't make sense. It's the length of a side of a box. So I only need to pick 2 test points, one here and one here. And what I'm hoping for is when I plug those test points into the derivative, that I get a negative followed by a positive, because that would show down then up and prove to me that that's a minimum. So my test points, this is where getting the calculator answer is good, because 2.9 tells you that you know something to the left of that, right? Like 1. And then something to the right of 2.9, like, I don't know, 3. You know, might want to go bigger than 3 if you feel like you're unsure. You could go 10, 4, 5, whatever. You're plugging those into the derivative, right? 1 and 10 into the derivative. So go back to the derivative, which was right here. Plug in 1. What do you get? Negative 288 over 1 plus 12. That's a negative number, right? So it's decreasing over there. So I'm decreasing here. Now plug in 10. Negative 288 divided by 10 squared. 10 squared is 100, right? So it's negative 2.88, and then plus 12 times 100 times 10 is 120. So it's a positive number. So that tells me, therefore, we have a minimum at x equals the cube root of 24. Once I know what x is, I know all the dimensions, don't I? Because x was our width, right? Our width was x, which is cube root of 24. What is the depth? It's 3 times that, isn't it? So 3 cube root of 24. That's what we said to start the whole problem, right? The depth had to be 3 times the width. And then what is the height? Well, that's our y value, isn't it? And we had an equation for y. Wasn't y 288 over, what was it? Am I messing this up? Hold on. Oh, sorry, yeah, it was up here, right? Here it was. 36 over x squared is what it was, right? That's what it was? That was what y was? So this is going to be 36 over x, which was the cube root of 24 squared. This is it right here. Those are the exact values. Well, I wouldn't need the decimal point. I would need that. You don't need to turn that into decimals. If you'd like to, you could. So what we've achieved in this problem is we've shown that there's a way to build a box to hold that amount of volume in a way that we use the least amount of material to do it. Think of another one. Which one? 2. Just got 1?
I don't know. I think I did it wrong, right?
Why? Why do you think you did it wrong? I think you did it right.
So that's right?
Mm-hmm.
Really?
Mm-hmm. Mm-hmm.
Oh, I thought it was 2 or...
It's kind of weird, because what you're saying is that what is it? Secant. Hold on a second. You're saying that secant x times sine x over tangent x is equal to 1. Which, well, it is. So it'd be kind of cool, like, I think it would be cool to, like, have, like, a birthday cake, you know? Instead of putting, like, that little wax candle that says 1 on it, you get a bunch of, like, wax letters and just put, like, secant X. Wouldn't that... There are infinitely many representations of 1. And some of them are simple and some of them are very complicated. And this is one that's, it's whatever, it's trivial. Here's one of our favorites, though. Math people love this one. That's one of math people's favorite equations. And if you look at it this way, you could rewrite it like this. That's another way of writing 1. 1 is negative e to the I pi. Now, the reason why we like it so much is because it contains all of the cool numbers in math, if you consider these cool. It contains 1, which is an important number in math. 0 is an important number. E is important. Pi is important. I is important. But they're all tied together through that equation. People say that's the most beautiful equation in math, but it's debatable.
This is my,
The one, not the one box, the one below it.
I want to see if you would have set this as the bonus answer.
I don't know. I have to work through it myself. Did you get to an answer?
I mean, I showed that what it would be. I was showing that.
Oh, this is what we just.
I was just proving that H equals D, and then so I created my minimum equation for the surface area,
Mhm.
and then I created a pretend problem of D equals 6, H equals 6, and I showed.
That it was true.
And what's crazy is that.
Did you do it in general though? Did you do it in general?
What do you mean? For which one? Like the actual creation of it?
Did you show that H is D
Yes. I showed.
with the derivative?
With the derivative.
Okay, so let me see. You have your volume is this, right? The surface area is that. You want the minimum surface area. So you want the derivative of surface area to be 0? How did you do it?
Because I manipulated the volume equals this. So
Yes.
with that,
And you replaced it in there?
2 pi r.
Yeah.
2 pi r equals 0, and then I have this.
Everything's in terms of R there now?
And I substituted my v in for the.
Mhm.
For the. Oh yeah, substitute. Yeah, the h was I substituted there plus 2 pi r, and then right here, I canceled out the pi r with this pi r. No.
Mhm.
Yeah. So it's just r underneath. Then I get plus 2 pi r squared. Then I had because what I was doing is that I was looking it up and I was trying to explain to me what's happening, and so I was just working along with it.
Mhm.
And then I got to this part, and I figured out why this equals that is because right here you can I'm just trying to because me and Anthony spent like 30 minutes analyzing this in the library, and from there we created our own.
So 4 pi r is diameter.
And then this is gonna be the height, and I know.
Why is that height? To me that looks like 2 pi height. Doesn't look like height.
Anthony, what did we come up with this one again? Can you come in? I remember we had a eureka moment in the library. Remember, because we were like looking at it, I was like, now why does that equal that? And we were trying to show how the 2 pi r squared. And remember, and I was like, oh, it equals that because of this. What did we say?
Y'all figure it out. We can talk in a second. What did you do from here to here? I'm just trying to figure out what you did. Oh, you split it back into 2 fractions, didn't you?
There's 2 here. Wait, no, can you do that? It's squared, so it's not like this times another one of these, and then one cancels, and then one cancels.
Mhm. But
Then it's this.
mhm.
Is that it?
This is, erase that for a second. Just erase it.
The whole thing?
Yeah, just the part that's boxed. Everything inside of it, sorry. I just didn't want you to erase everything. Okay, that's good. Yeah. So look at the numerator. What is that?
Should I have looked at that? But there's like an equal. Oh, well, there's right?
What does sine squared plus, what is sine squared x plus cosine squared x always equal to? 1. So that's just 1 over, and what's that?
Cotangent.
1 over cosine?
Wait.
Secant. Done.
Were all the other steps that I did necessary?
Uh-huh.
Everything was necessary.
Common denominator.
And all this
Yep.
junk.
Yep.
Okay.
That was good.
Well, I'm glad that I understand that when I look at it.
That's good. That's good.
I think I figured it out. Your watch goes off
Every hour?
Yeah, every hour. Because, like, I don't know, every time in class I hear it go off. I've been hearing it today.
It's annoying, huh?
And then I look at the clock and I'm like, oh, okay.
Yeah, it's a little off from my computer. I like to be ahead of everybody. Okay.
Okay. So basically here, what happens is that you take the derivative of it. So we bring the r up. So it's r to the negative 1 power. Bring that over. Then bring it back down. So it's negative 2v over r squared plus 4 pi r. And then we have the v equals this. So we just substitute that back in. 2 pi r squared. We know that a radius is a diameter equals 2 radius. And to prove that h equals d, for r has to be 4. That has to be 4 radius to equal h. And so that cancels out. You have 2 pi h. And so 2 pi h, 2 heights. Or no.
You're overthinking this a little bit. Divide both sides by pi. Divide both sides by 2. And what do you get?
Okay.
What?
You get h equals 2. Wait, no.
Yeah.
Oh, yeah.
H is 2r.
Yeah, which is the same as saying
H is d.
So
That's right.
That's
There you go. That's what you're trying to tell me right now. Yes, I totally agree. But show it with the lines. You don't want to get to a point like this and go, oh yeah, and all that stuff you just said. Just show the algebra. I mean, at the end you should get h is d. And you can do that. Just do a couple more lines, and that's it. You're done.
So,
That'd be okay.
So then we had our minimum. So would this be cool for like?
This is what I want.
Oh, you wanted this?
This, I want it in general. I want the general proof for any volume. Yeah.
Can you show me how to do the general proof?
You just did.
Oh, that is the general proof?
That is it.
Oh, okay. I thought you were saying that this was like.
No, I mean, because you didn't fix the volume, did you? You never told me like volume was anything, but when you differentiated, you treated it like a constant.
The reason I didn't know if we should treat volume is because you said do not use 1 liter. So
I didn't want you to pick a specific volume.
Oh, okay. That's why.
Because that would have shown it was true for a 1 liter container, but it doesn't show it's true in general.
That's why I just used V. So I was like, okay.
That's exactly what you have to do.
Okay.
So you've already done it. You did it exactly what you were supposed to. Nope. Nope. Just like that. Yeah. But go fix that last part. Just go add the little. Okay. All right. What else do y'all want to look at? Or are y'all done? Are y'all burned out? What? You're not burned out? Of number 2? Okay, so which one? You pick. Okay, 2a. Y is equal to x plus 1 to the x. Yes. Now, let's all be clear on one thing here. We are taking derivatives now, right? We're not doing limits right now. We're taking derivatives. So this is called logarithmic differentiation. Now, the thing that should clue you into it is the fact that you have x's both in the numerator and denominator. I wouldn't. So just look for that sort of thing. You look for x's both in the top and bottom. All right? Because think about it. If this was like x plus 1, let's say to the fourth power, you could take the derivative of that using chain rule, right? 4 comes down, you do something to that. But the problem is this is not a number, it's a variable. And that's what makes it so different. So we're looking for that both in the top and bottom. So I say natural log y equals, then again, you put the natural log in there, but that's going to allow you to drop that x out, right? So I was saying be careful, this is not a limit anymore, because I don't want you saying, oh, we do this and then we drop this underneath. That's not what we're doing. We're taking the derivative now, right? And so we're going to do implicit differentiation right now. And it'll be product rule. That's what you're saying? Yes. So I'm going to do this. This is what I always did whenever I was doing implicit differentiation. So what is the derivative of natural log y? 1 over y times y prime. And then over here on the right side, product rule. All right, what is the derivative of x? 1 times natural log x plus 1 plus, what's the derivative of natural log of x plus 1? 1 over x plus 1. Now you do have to also do the derivative of what's inside, but it's just 1. So who cares about it? Times, finish the product rule off, x. You can do it now. Y prime equals, I'm just going to write it as y right now. Natural log x plus 1 plus x over x plus 1. Do you believe you're the only one who came from pre-cal? Mm-hmm. Mm-hmm. Yeah. That's the final answer. I can write with both hands. I can't write well with both hands. Ambidextrous. My grandfather was ambidextrous. Not me, though. This is the cleanest one right there. Yeah.
So if I put that, you would have put it that way and counted it wrong?
I would have boxed this. I would have, on your test, I would have boxed that and scratched that, and I wouldn't have taken any points off. Yeah.
But this would be wrong.
Not completely there.
But there'd be points taken off, right? I don't know.
8 out of 10 points you would get.
Okay.
It couldn't be 100. You know, it couldn't be perfect because you'd go a little further, but you're pretty close. I'm just not sure how you're convincing yourself that that's true. Let me give you another suggestion. Maybe at this point, no.
Is that not true?
No, it's not. Because you'd have to do 1 over this minus this over this. You have to separate it in 2 fractions.
Okay, so this over this is
Mm-hmm.
tangent.
So that's that.
1 minus tangent.
But this one has this below it too. You have to look at both of them over this. So it would have to be this over this, then minus this over this. So you would need this 1 to still have the cosine to the 4th x under it. Yeah. So I think you need to start that one over.
No.
I know.
Wait, it's supposed to be like that?
Mm-hmm. Yes, but you're going to be right back where you started because look, this is this. And then 1 over cosine is secant, and you're going to be right back to where you started. That's why I say I think you should start over. I don't know. Try to turn your secants into tangents, or the other way around, using your Pythagorean identity. Which one? You don't want me to do another one of those? How about I do D, 2D? 2D? All right. Oh, were y'all okay with this one? Okay. All right. These aren't that bad, in my opinion. I think once you catch on to them, they're, should I say, fun? No, probably not. My gate code? Really? Gate for what? Huh. Man, I tell my students too many things if I'm giving them my gate code. Yeah. Oh, yeah, yeah. My neighbor and I are, you know, like my neighbor, we share, like we bought a big old riding lawnmower. We pitched in. We both went half on it, and like we have it in the shed, and all of our combination locks in the back are all the same. And yeah, exactly. What is the code? I'll just say it's an irrational number. It's the first few digits of an irrational number. All right, so look, we could differentiate this. Pardon? We've talked about if it happens, we'll work it out. Yeah, you know, we'll devalue it, whatever we think is fair, and whoever stays keeps it. Yeah. I don't know how we would do that. We would come up with some valuation on it, just Craigslist it or shop it online and see what it's worth nowadays used. Not the full value of it, though. That's what I'm saying. It was $3,000 when we bought it. So. Oh, no. Slash the tires and shit? No, that's not what I meant. It's, yeah, big enough, I guess, to want to ride around and not push a mower. It's about as big as this room. No, I'm kidding. Yeah, it's the zero-turn ones. Those are fun. Yeah. We have pretty relatively large yards. They're not huge, but hilly, lots of trees. When I mow my grass, I mow his. When he mows it, we like switch off. So it's like, you know, it's just kind of, we have a lot of, our fences go on a green belt. So we also maintain about 15 to 20 feet behind our houses too. And it's probably, I don't know, 700, 800 feet of both yards. I don't know, an hour. Yeah, that's the part that sucks. Okay, look, derivative. All right, derivative. You could do this with quotient rule, but it would be like derivative of the top, right, times the bottom, minus, and derivative of top is a product rule with a chain rule, and the bottom is going to be power rule, chain rule. It could be a mess if we try it directly, right? Do y'all see that? But if I come in with the natural log on both sides first, then I can use properties of natural logs to clean this up and make it much easier to do. Yes, the division becomes what? Subtraction of two logs. So natural log y equals, now I'm going to have two logs, log of the top minus log of the bottom All right. Everyone okay with that? Now, you still would not necessarily want to take the derivative here because this is still not that nice. But on this first one, do you see you have a product inside of a log? And so you can break that into 2 logs. And this one, the 2/3 can come down. So what's happening is it's just getting nicer and nicer and nicer and nicer. So I broke this up into 2 logs. I also rewrote the square root over this as all of that to the 1/2. Why? Why did I rewrite the square root as all this? Because I'm going to bring that power 1/2 down. I still have natural log y on the left. No go. See if you can take the derivative of this, and I'll check to see if we get the same thing. Because we're ready at this point. There's nothing more we can do. We can't split any of these logs apart. We've pulled all powers out, but it should be pretty clean, you know, natural log of x. The other one's a little chain rule. I don't either, but we've got to try something, okay? Like, I have an idea. No, I didn't. What problem is this? See, these are Christie's problems, so I didn't make these. So I don't know exactly what to do, but I'm going to try something. Okay, so look. That's okay. Okay. So can I tell you what I'm thinking here? I am, but I'm just curious what'll happen here. I'm only curious, all right? I'm not sure I like this idea yet. Do you agree that that's the same? Yes. Okay. Now I have secant squareds and tangent squareds, and I have Pythagorean identities for that, right? So let me try and get everything in terms of secant or tangent, my choice. Your choice. What do you want? Tangent? Okay. You want to turn these all into tangents? Okay, so secant squared is going to be replaced with 1 plus tangent squared. Yes? And then I had a tangent squared there already, didn't I? Okay, and then this, I'm going to get it? Right. What happens over there? Right? And then this is just a 1. So that's just 1 times, so it's just this now, right? This is 1 plus 2 tangent squared x. I'm kind of happy with that. Yeah, I don't really think I want to do anything more to that. Yeah. Move on. I'm very, very unlikely to give you a problem like that. Okay, just move on. So go there, but on this next one you do need to do this one. Square root. It, not yet. It was secant. You're supposed to replace it with secant theta, secant x squared, and then minus 4. You just forgot your x, right? What happens when you square that? No, when you square the 2, you forgot to square the 2. You square the 2 and the secant. Did y'all get this? All right? That's what you should get there. Yes. Just bring it with me. Oh, I didn't do a derivative yet. I didn't do a derivative. All I did was I just brought the 1/2 out. Okay, I haven't done derivative until this line, and I'm missing something also. The derivative of the left side. Right? This was equal to 1 over y prime. Right? 1 over y prime. So you have to take this and multiply this by what? By y. So your final answer is this multiplied times this nasty thing right here. From here to up here? Yes? Can you hold on for a second? Well, y'all hold on for a second. You square them both. Yes, but what you're doing is you're taking that 2 secant x and you're plugging it in, right? And squaring it. So you square the 2 and the secant. So it becomes 4 secant squared x. You square them both.
Okay, so if you have something like this, okay, that's what it was, right?
Mhm.
And if you plug something into that, like say you plugged in a 4, it would be like this, and then this, even though it's the same thing, like it would look like this. That's wrong. I mean, it's not wrong, but it's wrong. Like if I should have written it.
What if you plug in a -4?
I was about to put a negative on it, seriously.
Yeah, so if you do that, you'd have to do that because that is not the same as -4. That's right. These are not the same. So when you're plugging in the 2 secant x, you have to put it in parentheses and then square each of them.
-4.
Yes, and then all under the root. Okay. Yeah, and then what I would recommend you do is factor out a 4. Right? What would happen if you factor a 4 out? Did you figure out that? Yes? Are we all good on this? No? Yes. Can I do what? 2b? 2b? Oh, yeah. Okay, so the left side was 1 over y prime, right? Okay, the derivative of natural log of x is 1 over x. Plus, now I have a 1/2, so I'm going to keep the 1/2 here. Times, the derivative of natural log of something is 1 over it. Times the derivative of what was in the natural log, which is? Yeah, I brought the 1/2 down. So derivative of natural log of this is 1 over it times the derivative of what's in there, which is 2x. And I'm done with that derivative on the middle one. Is that all right? Okay, what about this one? -2/3 just sits here. And then the derivative of natural log of x plus 1 is 1 over x plus 1 times the derivative of x plus 1, which is 1. And things start to clean up, like this 2 and this 2 cancel. And I'm left with just 1 over x plus, I still have an x here, so x over x squared plus 1. And then over here, I just put the 2 on top there. 2 over, and then the 3 on the bottom with the x plus 1. Does that make sense now? Yes. But then that's all 1 over y prime. So I multiply both sides by y. So it'll go away on the left side, right? Y goes away over here, and I put y on the right side. And y is the actual original ugly thing. So that's your answer, the right side there. You don't have to do anything else with that. Box it up. Okay, so you said you wanted me to do 2b? Yes, yes. 2B. All right, I'm going to go quicker through this one. Natural log of y here equals natural log of natural log x to the natural log x. So I took natural log on both sides. I'm going to pull the power out, right? The power is the natural log x. That's what I'm pulling out. So I have natural log x times natural log of x. So be careful, like what's multiplication and what's composition. This was a natural log x. I'm pulling it out. There it is, times whatever this is. And now I'm going to do my derivative. Left side, 1 over y prime. And then on the right side, take it easy. All right. Product rule, right? Product rule here. So derivative of natural log of x is 1 over x times log of log, right, of x. Yes, yes. So the derivative, it's chain rule here. So we have natural log of something. So the derivative of that is 1 over what was inside of it. So 1 over, well, what's inside of it? Natural log x, times the derivative of what's inside of it, which is 1 over x, then times the one that was in front for product rule, natural log x. And these natural log x's cancel because they're separated by multiplication. And so you have natural log x all over x plus 1 over x. That's all that's left over there. But then I need to multiply that, both sides, by what? Y, but y was natural log x to the natural log x. I'm moving quick through that. I'm hoping, you can go back and reference that if you need it. I'm recording everything I'm putting up here, by the way. I don't know if those of you who came in here. Oops, sorry, I should have told you that. So if you want to go back and watch any of this, you can. What? Where did I get what? This? That's y. Remember? We're always going to have to come back in with y on this side. All right. Which one do you want? B? Take the derivative of b first. This. Okay, good. What's that? Here. Pythagorean. Do you want me to go back through the video and edit out all your... No? Okay. That's way too much. Yeah. No one's going to care. All right. I'm going to make it a private video. No one can find it except my calculus class. All right. Pythagorean identity right there. What is secant squared x minus 1? What is it? Move things around to make it look like what you have there. You have a secant squared x minus 1. So can you make this look like secant squared x minus 1? Yeah, well, I figured you'd knock that out first. You'll need it. What does the mean value theorem say? Yeah, the mean value theorem, the idea behind mean value theorems was this. If you have a function that starts at a point A, ends at a point B, it says that the slope of the line connecting the endpoints, and that slope, you could find the slope of that line by doing rise over run, which would be f of b minus f of a. That's your rise in your function, divided by the run in the function, which is your left and right. That should somewhere, there should be somewhere on the graph where the slope of your tangent line is parallel to that. Do you remember that picture? All right. So what we are trying to find is the place on our graph where the slope of our tangent line is equivalent to the slope of the secant line connecting the two endpoints. Remember this? Okay. So on part B, I give you y equals x plus 1 over x. I give you a closed interval 1/2, 2. Did you get tangent? Good. And it's underneath the square root, right? No, you can do the square root of, this is tangent squared, right? Square root. They kill each other off. It's just tangent. You have 4, this turned into tangent squared, right? Like this. So what's square root? It's because it's multiplication. What's square root of 4? 2. What's the square root of something squared? See, this and this will cancel. And you just get tangent. Thanks. I doubt it. I doubt it. I would definitely start working on, look, you should probably start with something like 8 and get through those. I would skip 7. It's probably not going to happen. Okay. So this is, first of all, this is our function, right? F of x, switch your y to f of x. The way you do mean value theorem is you just first figure out what that side of it is. What's f of b minus f of a over b minus a. So in the problem, a is the, a and b are the endpoints of our closed interval. Those have to be given to you, right? We're also supposed to check that this function is continuous on the closed interval, or else mean value theorem doesn't work. And we don't have to worry about that because this is defined everywhere except 0, and our interval doesn't have 0 in it. I'm not going to try and trick you and give you one that doesn't work, okay? But I'm just pointing out that you would have to look at that condition. All right, so what is f of b minus f of a over b minus a? For us, that's f of 2 minus f of a half over 2 minus a half. You actually plug it into this function. So what's 2 plus 1 over 2? So what's 2 plus a half? 5 halves. Just going to trust you could do that. 5 halves minus, now if I plug in a half, what's 1/2 plus 1 over a half? Well, 1 over a half is 2, right? 2 plus a half, right? It's 2 plus a half. 2 1/2, which is 5 halves again, isn't it? All over 2 minus a half is 3 halves. All that really doesn't matter because it just comes out to be 0, right? So now what you say, whatever this number is, in this particular problem, it came out to be 0, didn't it? But if it had come out to be 2 or something else, that's the number you're going to use in just a second. I need to figure out where my derivative is equal to that. So I need my derivative. Did you all find your derivative? And we can do it at x, but the mean value theorem, they like to use c because we're trying to find the value c. So what's the derivative at c? It's 1 minus 1 over c squared. Do you agree with that? The derivative of this is 1, and then derivative of 1 over x, we've done it like 3 or 4 times today. It's negative 1 over x squared, so negative 1 over c squared. So I want to match these. I want this to match up with this. So 1 minus 1 over c squared to be equal to 0. And you can move things around. I'm out of room here, so I'll go up with this. This is 1 equals 1 over c squared. I'll multiply both sides by c squared to get c squared is 1. I take the square root, I get plus or minus 1. So move that over, multiply both sides by c squared, take the square root, 2 possible answers, right? But the interval is only 1/2 to 2. So I only have one answer. It's at 1. Understand? Multiply, what, here? From I multiply both sides by c squared. And then it becomes c squared on the left and cancels on the right. And then I square root it to get to here. We good? So just 1. Because I believe that the problem asks for you to find the value or values. You could have more than one. Like if our interval would have been bigger, you would have included both answers. So it says find the values of C which satisfy the theorem. You've done that. Now what if this over here had been -3? What if this over here would have turned out to be -3? Then you would have had something like this. 1 minus 1 over c squared must equal -3, right? The c is what we're concerned about. And don't worry about the interval, okay? Just I'm saying, what if that difference quotient on the right side, we got 0, didn't we? What if it would have turned out to be a number like this? Well, you just still have to solve this equation. So I'll move the 3 to the left, make it a 4. I'll move the other one over, I'll make it that. 4c squared equals 1. I would divide both sides by 4. I would take the square root, and I get plus or minus 1/2. And then well, this is a different problem because I changed what the right side was, so it wasn't those two endpoints anymore. But just to show you that this equation that you end up with can turn out to be different depending on what that right side is. All right. Look at another one and see. Are you doing okay over there? Oh, see, you're doing those all right. Well, these are verifies, right? So you know you're right, right?
Yeah, but can you make sure?
I will, but I mean, you've.
Yeah, I understand what you're saying.
Common denominator. Good. Okay. Good. 12:35, folks. We probably have time for another one. If you haven't asked for one, you got something? No? Anyone? All of them? Mm-hmm. Mm-hmm. Well, that's always an option. It's not. If it turns out you're trying to find x-intercepts, you're setting the function to 0. If it's a polynomial and you can't factor it, the only thing you have is synthetic division. I haven't made the test, so I don't know if I can't tell you if there will be. I wouldn't intentionally make a problem that you can only factor with synthetic division to get the x. I mean, it's not. Only one. Yeah. Oh no, not even close to 20 questions. No. 1, 2, 3, 4, 5, 6, 7, 8 to 10 questions. Bonus. What do you? All of a sudden, the bonus came in out of nowhere. Where'd that come from? Really? Huh. I gave you a take-home bonus. You got it. Yeah. Yeah. It's an optimization problem like that box problem we just did. But you have to show that if you want to make a cylinder, like a cylindrical can, that no matter what the volume is, no matter how much you want it to hold, the way you make it to use the least amount of material, so to minimize your surface area, is to make it so that the diameter is always equal to the height. So show that a can that's diameter equals height is the optimum way to build a can. Yes? There's nothing on that screen. Right here? I know that this review is a bit overwhelming as far as there's a lot here, but I felt like it was, you could practice a lot, but please do not ask me to finish the key on this or something like that. I mean, like, I do not feel like doing 6 graphing problems, and that's a lot of work. So I don't mind doing a graphing one, but it's your call. How to get what? This? Oh, over here. I moved it to the other side of the equation. Yeah, I added it. Okay, I see that the problem is this right here is 1 over cosine x, but not minus 1. This minus 1 is not with it. So you need to write it like this. 1 over cosine x minus 1. You see what I'm saying? And that's going to be good because I bet you can get a common denominator there, and I think things will probably turn out to be decent. You know what I'm saying or not?
Yeah, I mean, I hear what you're saying. I don't know if I know what you're saying, but I hear you.
Secant x minus 1. This right here is 1 over cosine. That 1 is not anywhere with it. Oh, what I said after that? Oh, yes. So if you're here, then yeah, go and try and do something to that. What do you got?
Oh, I was just going to ask again what you had told me, because I forgot what you had told me. So you said, okay,